For our next application, I want to think about a situation where we have a container of water. Maybe it's an aquarium in your living room, pool in your backyard, maybe it's the ocean. Okay, and I'm going to take a flat plate and I'm going to suspend it in that container somewhere. And I want to think about the pressure that's being exerted on this plate. Well, if the plate is horizontal like this, it's pretty straightforward. There's a column of water above the plate. That column has mass. It exerts a pressure on the plate going down into the ocean or towards the bottom of the container. That pressure is equal to W times H. W is the weight density of the liquid, and that's going to vary depending upon what kind of liquid we're talking about. And H is the height of that water column. So the weight density, that's usually going to be in units, something like pounds per cubic inch. And if you multiply that by height, say inches, you get pounds per square inch. Yeah, that's a pressure. Those are pressure units. Okay, good. Where things get interesting is when we start to rotate that plate. Okay, turns out that no matter how that plate is turned, the pressure being exerted on it stays the same. It's always going to be W times H. And there's a name for this. It's called Pascal's principle. It's named after a French mathematician, Blaise Pascal. And the principle states that the pressure exerted by a fluid at a depth H is transmitted equally in every direction. So the downward pressure on the horizontal plate is exactly the same as the horizontal pressure on the vertical plate. It's the same no matter how the plate is oriented. So what we'd like to be able to do is to take this principle and calculate the total force being exerted on one of these objects. And so to do that, we're going to need one more formula here. Force is equal to pressure times area. For example, pressure is pounds per square inch times area, say square inches. Yeah, okay, that leaves us with pounds. Exactly what we would expect to happen. Okay, so I've got a situation here for us to kind of model this with. I have an irregularly shaped object and it's suspended vertically in a tank of water. And to answer this question, I need two things. First, I need a function that describes the depth of the object for a given value of y, or y, as it always is going to be our vertical axis. Now, if we put the x-axis at the water line, then 99% of the time, this is just going to be negative y. Right, but we want to trying to be general. There's maybe some weird situations where it's something else, right? So I'm going to put a function here, and just kind of understand most of the time negative y is going to get substituted in there. The second thing I need is a function that tells me the length. That's the distance across the object at a depth of y units. Right? I put these two things together, and we should be able to answer our question. I'm going to do this the way we have done so many things up until now. I'm going to look at a narrow horizontal strip taken from the object, and I'm going to calculate the force being exerted on that strip. Right, then I'm going to add them all up. We'll take a limit, turns into an integral, and we'll have our final answer. So if we call this the ith subsection, then the force is equal to the pressure, which is W times d of y sub I. That's Pascal's formula, right? D of y sub I is the H, times the area, which is L of y sub I. That's the length of the rectangle, times delta y. That's the height of the rectangle. Okay, so if we add all of these up over all the values of I, right, all of our subintervals, we get this approximation for the total force, W times L of y sub I, d of y sub I, times delta y. And if we take the limit, as n goes to infinity, the left-hand side is just f, and the right-hand side, the sum becomes an integral. And we get our final answer. The total force exerted by this fluid is equal to W times the integral from a to b of L of y, d of y, dy. Right? That's going to be our formula. Okay, so let's take a look at an example. I have an aquarium and it has a giant glass wall that's 50 feet wide at the base, 80 feet wide at the top, and 50 feet tall. So the wall is in the shape of an isosceles trapezoid, where the base is centered with respect to the top, right? But it's kind of upside down. So the small base is on the bottom, the big base is at the top. And I want to know what's the total pressure on the wall if the weight density of seawater is 64. It's going to have to be, what, 64 pounds per cubic foot. Okay, so like I said, d of y, we're going to put our x-axis at the water line. So d of y is going to be just negative y. And the next thing we need to do is come up with a formula that describes the distance across this trapezoid at a given y value. Okay, so what I want you to notice here is that at the top, when x is equal to 0, we're at the top of the wall, and the width is, 80 feet. When we get down to the bottom of the wall is at negative 50, and the distance, the width at that point is 50 feet. Okay, so if we find the line through these points, right, we'll get a function that describes the length. So the length is going to be, you can find the equation, find the slope-intercept form. It comes out to 0.6y plus 80. So again, you kind of test this out, right? When y is 0, this gives me a length of 80, and that is the width of the top. And if I put negative 50 in there for y, 0.6 times 50, that's negative 30 plus 80. Yeah, it's 50. Good. That's the width of the base. This is doing what we needed to do. So now it's just substituting into the formula. The integral becomes 64, that's w, times the integral from negative 50 up to 0 of negative y times that L of y function, dy. And now it's all downhill. This is a pretty straightforward integral. I'm going to distribute the y, and I actually pulled the negative out in front. You notice the 64 became negative. Now we can do the antiderivatives using our power rule. And if we substitute these values in, if we put 0 in there for y, it becomes 0. And if we put negative 50 in, this comes out to a grand total of 4.8 million pounds worth of force being exerted over the whole of this giant glass wall. So we've got one more physics application we're going to take a look at. We're going to see how we can calculate something called the center of mass of an object. The center of mass, it's kind of the point where you can act as if all the mass in an object is concentrated. Have you ever seen somebody spinning a basketball on their finger, or one of those vaudeville acts where they're spinning plates on top of these tall, thin sticks? The point that the ball or the plate is resting on the finger or the stick, that's its center of gravity. So that's the point that we're going to see how we can calculate, again, using these integration methods we've been discussing.